So we stopped last time talking about how kinetic energy is transferring heat, is transferring kinetic energy from one mass to another. Let's talk about methods of heat transfer to happen in the atmosphere. So the first method that we can see is radiation. If you've been outside in the winter and you've gone skiing or done some other kind of winter activity, you know that you feel the warmth of the sun on your face when you're outside. It's cold outside, but your face is warm. My dad and I, we were ringing bells with the Salvation Army last Saturday at a grocery store, which happened to face kind of the south. And as the sun came out from behind the clouds, even though it was in the 30s, we felt pretty warm outside once we had that radiation from the sun hitting our faces. And we felt a lot better about that until the sun went behind the cloud, we lost the radiation, we started feeling cooler. But we could feel that radiation from the sun hitting our faces. The next type of heat transfer that we can see in our atmosphere is conduction. This is molecule to molecule within a substance. So if you think about burning a log on the fire, I have a burn pile in the backyard, we live outside city limits. We put some logs on there. Sometimes they're a pretty long branch that falls out of a tree, and you got a good fire going in the middle. You don't want to come up and touch the end of that log. It may look like it's not burning. Maybe part of the log is burning, but part of the log is not. Reaching out and touching that log, you might still burn yourself, because conduction is molecule to molecule transfer within that wooden log. Even though one end's burning, one end's not, the other end of the log is in fact hot. So conduction is molecules transferring within a substance, such as a wooden log that's on fire. Okay, the third type is convection. So that's heat transfer of mass movement of fluid. So think about a cake baking in the oven. I like to bake. I like to make cakes. In my oven, I have air that circulates around that cake that's sitting in the pan, and it's baking. That air is circulating heat around. It warms the batter in my cake pan, and I get a delicious cake when the cake is done baking. Now, that might raise a question in your mind. Is something else possibly also going on with baking that pan, or baking my cake? Well, there is some conduction going on too, because we have a metal pan that's transferring molecule to molecule in that pan and warming up. This is why, personally, I like to bake with a thicker pan, because it insulates things better. But there are advantages and disadvantages to using various types of materials. So, radiation. Everything above 0 degrees Kelvin emit radiation, and we looked at the temperature scale in the last video. Anything that is radiating, it is going to be above 0 degrees Kelvin, and it emits radiation. Now, with a higher temperature, it's going to emit a shorter wavelength radiation. And I want to show you an example here in a minute on a toaster oven. The short wave is enough to stimulate that visual color that we're going to see within our toaster oven. And I'm going to pause the video here and get it set up to show you that radiation here in a minute. Hopefully you can see inside my toaster oven here. And you can see that if I look inside at the coils inside of this toaster oven, they are glowing. They are emitting radiation because they have energy, and our shortwave radiation is hot enough to stimulate that visual color that we see, that red glowing in there. So we saw how the toaster oven had that shortwave radiation and stimulated the visual color that we see. The sun is really hot and has very short waves. Now, some different objects, like the Earth's surface, is made up of different surfaces, water, land. They absorb radiation at different rates. And we are going to get into that here a little bit more detail. One example, just to give you first example, is snow absorbs infrared radiation, but not sunlight. So we call it a selective absorber. So as the Earth's surface and atmosphere heats and cools in different ways, this is really a huge producer of weather for us. So we're going to look at some ways that solar energy affects the surface of the Earth. Now just take a minute and write down on a piece of paper that you're using to take notes some things that change the way solar energy affects the surface of the Earth. What kind of things can you come up with? Now, some of the things that affect how solar energy reaches the surface of the Earth are that the Earth is tilted. So it's on basically a tilt, and I've got my globe here, which kind of shows that the Earth is tilted. We have the distance from the Earth to the Sun vary as the Earth travels around the Sun in orbit. We have different parts of the Earth are more water than others. So the Pacific Ocean, there's a lot of water in this area versus this part of the world, Africa, takes up a large portion. We also have the way the Earth turns. We have daytime and nighttime. So all these things go into how solar energy affects the surface of the Earth. Now, Earth's tilt. The Earth's tilted at 23.5 degrees, and this is really, really important for us because it affects how much energy of the sun gets absorbed, because part of the year the light is hitting the Earth at a more oblique angle, so not directly. The tilt of the Earth also makes our days longer at some parts of the year and shorter at some parts of the year. And on longer days, more sunlight gets absorbed by the Earth. And we see this as the days get longer or shorter. If you ever make a sundial, you actually have to calibrate that sundial by what time of the year it is, even by the month and the latitude that you're located at, or the sundial will not be correct. And that's because of the Earth's tilt. So the point at which sun's radiation strikes the Earth at 90 degrees actually moves north and south of the equator by 23.5 degrees, north latitude and south latitude, depending on the time of the year. And we're going to be talking about this in future video here. So at either equinox, daytime and nighttime are of equal length. So we have the vernal equinox in the spring on March 20th, autumnal equinox September 22nd. This is where the day and the night are equal length. At either solstice, so I'm recording this in December, we're approaching the winter solstice on December 21. That in the northern hemisphere is going to be our shortest day and our longest night. But if you're in the southern hemisphere, that's going to be your longest day and your shortest night. And that is because of the tilt. So if you look at this diagram here, I'll get my pointer. We can actually see here how on the winter solstice, the northern hemisphere is tilted away from the sun. So the sun's rays are hitting us at more an oblique angle, meaning that it is colder at this time of the year. Southern hemisphere is getting more of that direct sunlight because of the tilt. So the tilt is really important to know about because it is a major cause of seasons. Because of that tilt, summer is going to be in the northern hemisphere between May and August, obviously. But interestingly, Earth's perihelion, the closest the Earth comes to the sun is January 3rd each year. But that's not when it's the hottest for us in the northern hemisphere, is it? No, January 3rd is in the dead of winter. Again, that is because in the winter, the northern hemisphere is tilted away from the sun at an oblique angle. So the reason that even though we're the closest to the sun on January 3rd, in the northern hemisphere, that does not make it the warmest for us because of how the sun is hitting us at an oblique angle because of that 23.5 degrees tilt. And we're going to continue the discussion on the next video.